Okay, well, thank you, Phil, and thanks for inviting me. It's neat to give a seminar that can be simultaneously heard on 3 continents, even if the time is not optimal in any of them. Good morning and good evening, everyone. I guess I have to press a button here. Unfortunately, my laser pointer doesn't allow me to do that. There, okay. All right, very good. Okay, well, the kind of modeling that I'll be talking about in the frequency domain is of coherent structures. So just to define that, by a structure, I mean a pattern or arrangement of elements, in this case in a fluid flow. And coherent means that that structure is persistent or likely to be observed. And those 2 things already tell us something important about coherent structures. When we have a structure, we imply a reduction of dimensionality. We can describe the structure as a whole instead of having to describe all the fluid parcels that comprise it. And likewise, because the structure is persistent, it must be dynamically important. So from an engineering point of view, unlike the sort of beautiful pictures of structures that make us want to see them, they're usually associated with things that we don't want in systems, such as structural vibration, unwanted weather, unwanted drag. In my lab, one of the applications that we work on is aeroacoustics, and typically there, large-scale coherent structures are also leading to unwanted noise. So if we want to model these structures, we typically do so by defining a mathematical basis that we can use to break up the flow field into a set of different components. And there are many different techniques, as you can see by all the acronyms that I've sprayed onto the screen here. And we can sort of break those different techniques down into 2 different classes. One are sets of modes that are really driven by an operator, by a mathematical model of the flow field. And we want that operator-driven basis to be good or optimal at representing the kinds of solutions that we're after. And then the other kind of modes are data-driven modes, where we actually just observe large-scale structures, and we want to somehow use the data to drive a good or optimal representation of them. So in this talk, I'm not going to give a lot of attention to any of the other techniques that were listed on the previous screen, but I'm going to restrict things to 2 techniques that I think go very nicely together, particularly when we want to think about turbulence in the frequency domain. And those are resolvent analysis and SPOD, which is spectral proper orthogonal decomposition. So the outline of my talk is as follows. I'll start by describing what SPOD and resolvent analysis are. I think many of you probably already know, but I'll go over the basic definitions. And then I'll tell you a little bit about looking for coherent structures in high-speed jets, and sort of compare and contrast what we get when we look at SPOD and resolvent modes for the jet. And then I'll look at how we can extend some of the concepts from resolvent analysis into the nonlinear domain, particularly for looking at transitional processes from laminar to turbulent flow. And then I'll summarize and tell you a little bit about some of the things that we're currently working on in the lab. So in each part of the talk, I'll have separate acknowledgements. So in this part, I want to thank Aaron Town and Oliver Schmidt, who were key in the work that I'm about to show you, and which was also supported by the ONR. So spectral POD is not a new thing by any stretch of the imagination. Like almost everything in the world of POD, it goes back to the work of Lumley in the late 1960s, early 1970s. So Lumley sort of introduced POD in fluids, and POD is a way of decomposing a flow field, the fluctuations in a flow field. So we've removed a mean flow, and we want to represent the fluctuations as a set of basis functions. And in POD, we sort of use data to drive those basis functions. And in fact, we solve a maximization problem where we try to find a set of modes phi such that we project as much as possible of the fluctuations onto, say, the first of those phi modes. So we try to maximize this quantity lambda. Lambda represents sort of the amount of energy that we capture in the mode phi, the amount of fluctuation energy that we capture in the mode phi. So in fact, if you solve that maximization problem, you find that in fact, the modes that you get are basically eigenfunctions of the correlation tensor. So the correlation between fluctuations observed at some point in the flow and fluctuations observed at some other point in the flow, x and x prime. So herein lies a subtlety that I'm showing you on this slide. Lumley introduces two kinds of POD, a space-only POD, where these modes are just functions of space, and we're only looking at the correlation tensor at one fixed time t. And through an assumption of stationarity and the averaging process that you see here, then this gives us a representation that's supposed to be good for different times in this stationary flow. But we can also define our SPOD modes to depend on both space and time, as I've done here at the bottom. And if you do that, all the algebra carries through in exactly the same way. But now our correlation tensor is the 2.2 time correlation tensor that we're finding the eigenvectors and eigenvalues of. And the associated inner products that represent the space in which we're doing this maximization are space only in the space only case, and of course space time in the space time case. So given that there are these two flavors of POD, space time and space only, why is it that space only POD dominates the discussion for so many years in fluid mechanics? In fact, the statement's not entirely true. There were some early proponents of the sort of space-time approach, including Bill George and the group in Poitiers, for example, who used this extensively throughout the 1990s, really mostly. But apart from a few groups, most people were doing space-only modes. One of the reasons for this is really the evolution of measurement techniques that we use in fluid flows. So up until fairly recently, we did not typically have time-resolved field measurements of a flow. So with time-resolved PIV, we eliminate that barrier. But up until then, we had things like microphone arrays. This is on the bottom left, shows Bill George's fabulous 152 or whatever the number of hot wires that he had together in a jet flow. This is a large microphone array that I worked on a number of years ago, where we tried to put as many microphones just around a jet as we could in order to record these kinds of space-time modes. So, given that turbulence is a space-time phenomena, and given that these coherent structures, one of the main aspects of them that we're interested in is their time evolution and the fact that they stick together over a finite time. And so this need to be able to describe coherent structures in a space-time basis led to criticisms of the space-only technique and led Peter Schmidt and others to develop the DMD technique and the sort of theoretical cousin of that, the eigenfunctions of the Koopman operator. So it'll turn out, as I'll show you in a moment, spectral POD, which is the frequency space version of this, is really for all intents and purposes the same technique as DMD, but it's performing DMD in some kind of averaged sense. So when we go back to the case of stationary flow, but we keep our desire to have space-time modes, we can still do so in an efficient fashion, because it turns out that in a stationary process, we can break the POD modes up frequency by frequency. So doing a little bit of math on the general POD relation tells us that we can find modes for each frequency independently, and that these modes are eigenfunctions and eigenvectors of the cross-spectral density tensor in the flow. So basically the Fourier transform of the time-retarded correlation. So this produces eigenfunctions that oscillate at a single frequency and optimally represent through the POD properties the second order space-time flow statistics. So spectral POD, as I said, has been around for a while. The title of it I took from the Poitier group in their publications, but there were some other techniques along the way that were also called spectral POD. So I just want to be careful to disambiguate that for you. But apart from that, the algorithms are now fairly well established for doing SPOD. You estimate the cross-spectral density tensor using the Welch periodogram method typically. We publish software for doing this. And in fact, you know, it requires quite a lot of data, right? Because you need both space-time data over a fairly long period of time. And so one of the nice things is that Oliver Schmidt has introduced a streaming version of the SPOD algorithm that can be used with very large data sets. So that's SPOD. This slide, which I'll just do quickly, is just an example of a flow that I won't consider in any detail. And this is a flow over a vertical axis wind turbine. And my colleague at Caltech, John DeBeery, and his student Daniel Araya were doing this project a number of years ago, and they had this nice time-resolved PIV data that they were taking in this cross-sectional plane that intersects the turbine. And they were doing the time-resolved PIV in 3 separate windows. So I worked with Daniel, and we computed SPOD of his measurements, and the results that we got are shown here on the plot. I'm going to try to see if I can animate this. Here it goes. So what I'm showing you in the middle here is the spectrum of this flow, the SPOD spectrum. So this is basically it's like the power spectral density, but it's for the entire fluctuation field together. And the 3 lines represent the 3 separate PIV windows. So you see that in the black window near the turbine, I register a very strong peak frequency at the blade passing frequency. And when we animate the pictures, hopefully I can make that play again somehow. Okay, there it goes. When you see that mode animated in time, you see that indeed it corresponds to flow structures that are shedding from each blade as it goes around. If we look at the other PIV windows, we don't see that blade passing frequency so strongly, but instead what we see is the emergence of a much lower frequency peak that in fact corresponds to a sort of standard bluff body wake instability in the wake of the turbine. And one of the nice things that you see from the bottom movie is that even though these 3 PIV windows were taken completely independently, not even on the same day of the experiment, they patch together very nicely, meaning that you know, it allows us to be fairly certain that we've got a good statistical representation of this dominant coherent structure that we see in the wake. So SPOD is very nice for these kinds of stationary problems where we have you know, coherent structures that are oscillating at certain frequencies in the flow. It captures them very nicely. So the other thing that's nice about SPOD is that it pairs well with the technique that's called resolvent analysis or input-output analysis. So on this slide, I'm going to present a resolvent analysis in the context of nonlinear equations of motion. It's often used in linearized analysis as well. But what I'm going to do here is take the full Navier-Stokes equations written in this kind of discretized form. So as if we're going to do CFD on those equations to represent it as a dynamical system. And we do the standard Reynolds decomposition into a mean and fluctuating components. We put that into the equations of motion. And if we average those equations, we get the Rand's equations. But if we look at the perturbations of those equations, we get this sort of nonlinear disturbance equations, which for a stationary flow, we can naturally write also in the frequency domain. And what that allows us to do is sort of regard the nonlinearity as, or the fluctuating Reynolds stress, if you like, as a kind of forcing term on linear dynamics. And we know that turbulence isn't a linear process. We know that nonlinearity is crucial in establishing the turbulent flows, its energetics, the energy cascade, and so on. But still, there are amplification mechanisms that seem to be very well captured through the linear amplification of fluctuations. So that's represented nicely with the resolvent framework. It's taken over here on the right into the frequency domain to form a kind of transfer function for turbulence that takes the forcing F. These are the nonlinear fluctuations in the background turbulence that are being amplified through this resolvent operator R of omega into some measured output Y. So resolvent is really, in a linear operator context, is really just a Green's function, right? In a Green's function, we would look at a forced solution of the equation and we would sort of excite 1 degree of freedom in the system at a time. So it's not the solution of the PD that's so interesting in terms of the resolvent analysis, but rather it's what you do with the resulting Green's functions. And what you do with them is you take the SVD of them. And this solves really exactly the same sort of maximization problem that the SPOD modes satisfy. But what is maximizing is the gain between some input field F and some output field Y. And so through the SVD, we get a set of ordered modes, orthogonal modes for both the input space, the F space, and the output space, the Y space, that are ordered in terms of their gain. And so presumably when structures undergo large gains, they're likely to be the ones that we would actually observe in a flow. The resolvent, I should mention, is already a powerful tool in stability analysis of laminar flows, sort of before it gains this traction in the turbulence world, looking at the mean flow of a turbulent flow. The application to the turbulent mean flow, I think my colleague Beverly McKeon probably described this in this same seminar series a few weeks ago, dates back to really the early 2010s, at least in terms of using specifically the resolvent framework. So one thing we can sort of say right at the outset is that the high gain resolvent modes in shear flows are closely associated with the actual observed coherent structures. So regardless of how we think of the forcing, we have this kind of, there's this kind of good similarity between the prediction and what you actually observe. But the hard part is actually modeling the forcing term on the right-hand side. And there are many different approaches that different people are pursuing along these lines. We have sort of mechanistic models where we look at the detailed sort of nonlinear interaction of the waves that we're predicting through the resolvent analysis. We try to close the loop in a sense on resolvent analysis. So those are very interesting, but there are also nice statistical and data-driven approaches to try to learn the forcing for the resolvent. So all of those are nice things. The thing I'm going to tell you a little bit about today is using a very simple Eddy viscosity model to model at least part of this turbulent forcing. That is also something that has a bit of a history and has been done by a number of other people in the community. So one of the reasons that I've kind of hyped this, these twin techniques in the frequency domain, resolvent on one hand and SPOD on the other hand, is that there's a really tight theoretical connection between them. So if we think about our resolvent operator and we form the cross-spectral density matrix in this case of the output, the resolvent operator relates that cross-spectral density of the output to the cross-spectral density of the forcing term. And so immediately you can derive some identities from this. For example, if you modeled the turbulent forcing as being white noise, which is probably not a very good model in particular, but if you were to do so in here, you would get an identity between the resolvent modes and the SPOD modes. So if turbulent forcing of the resolvent acted as a white noise forcing, then one would get the SPOD modes as the output of the resolvent. So the converse of that is that we get information by comparing resolvent modes and SPOD modes. We can uncover information about how those modes are actually forced in the flow. So that takes me to the next part where I want to tell you about looking at coherent structures in jets using these two techniques. There are a number of other people that I need to acknowledge for this part, Ethan Pickering, George Regas, Guillaume Bress, and Peter Jordan, who have all contributed in deep ways to what I'm going to show you. So Guillaume Bress is responsible for the data that we've been using in this project, and it comes from some really marvelous large eddy simulations that Guillaume did now a number of years ago, and we've used very extensively ever since. We have a whole sweep of different Mach numbers for turbulent jets. These are sophisticated LES computations that include the nozzle. They include synthetic turbulence generation within the nozzle so that we have turbulent boundary layers right from the get-go. The goal in this project is to do modeling that's relevant to full-scale aircraft engines, and so we need these very high Reynolds number jets that have turbulent boundary layers. So the LES has come to the point where that can be done fairly reliably. And then all the acoustics that we're after in this project have to have a whole nother sort of set of computational techniques that are quite advanced and quite good in the Cascade code. So Cascade performed these simulations. I'm just showing you a visualization here. You can already see lots of coherent structure in this jet. And I'll come back to sort of some of the patterns that we see here in the data in a few moments. So let me just quickly take you through the SPOD process as applied to data from that jet. So we collect many, many snapshots from that jet. In this case, we did 10,000 snapshots for a Mach 0.9 jet, just as an example. And the SPOD process is the first, of course, as in any POD process, you want to exploit whatever spatial homogeneities you have in the problem. So we break our jet up into azimuthal Fourier modes first. And then for each azimuthal Fourier mode, we proceed to do the SPOD analysis. So that consists of binning up snapshots or creating segments of snapshots. And for each segment, taking the Fourier transform of that segment in time, and then forming from that the cross-spectral density matrix through averaging over those segments. And then with that matrix, we then find its eigenvectors and eigenvalues that give us the SPOD modes. So in the bottom right picture, that process has been completed. And you're seeing here a first azimuthal mode, m equals 1, dominant SPOD mode from this data set. You see it's a very, very clean representation of what in jets we call a wave packet. It's basically the Kelvin-Helmholtz instability mechanism acting on the mean shear to amplify and decay as we move down the jet column. This is showing you that mode at a particular frequency of a Struhal number of 0.35. So I've listed here some parameters associated with the data processing that I won't focus on today. So what I want to do is now take you through kind of a quick tour of the jet as seen through the SPOD, and then quickly start connecting that with what we get by predicting the modes through the resolvent analysis. So there's a whole lot of detail that I'll have to skip in order to show you this in a reasonable amount of time. And one of those details is how we actually compute the resolvent modes. A number of people that are on this call I know are computing these modes. A number of people in the community are, and I just want to stress that it's not a very simple computation, and there are lots of details that one really needs to keep straight to get good results out of a resolvent calculation. I may mention, if time permits, a few of those details later on in this talk. But right now, as I said, this first plot that I'm showing you is just from the SPOD spectrum, and what I'm showing you here is restricted to the first, the axisymmetric mode of the data. And we're looking at the dominant SPOD mode and the first subdominant SPOD mode as a function of Struhal number. That's the jet non-dimensional frequency going from high to low as we go from top to bottom on this plot. All you're seeing here is the x-axis is x, the streamwise direction in the jet. The r-axis is radius. And this is an axisymmetric mode, so you can just wrap this around the x-axis. So these are wave packets, and this is where we really started with the jet, because we've been modeling these wave packets in jet using other kinds of global techniques like linear stability analysis and parabolized stability equations. So one of the first things we could do when we got the resolvent was to compare the wave packet structures that we get with the resolvent with those from the other analyses. And for this case, you wind up getting very good predictions from a number of much simpler techniques because in fact, the mechanism behind these modes is the Kelvin-Helmholtz mechanism. And what you can see when you look at the SPOD spectrum is that comes out as a low rank feature in the data. It's much more energetic over this range of frequencies than other things in the data. So when we plot our SPOD spectrum on the bottom left, this is sort of a waterfall plot of all the different SPOD modes as a function of frequency. And you see that top mode has this bump up over this frequency range. That's our sort of Kelvin-Helmholtz response of the jet. But what turns out to be interesting in the resolvent analysis is now that we have this global view of the jet, it turns out that there are a number of other mechanisms that had mostly gone unobserved in turbulent jets. And so I want to sort of take you through those now, and I'm going to do that on a kind of busy set of plots where I'm going to compare resolvent and SPOD modes together. So the SPOD spectrum here is the energy of the SPOD modes, the lambda, and the resolvent is the gain spectrum, the sigma values. So they don't have any direct correspondence to each other. They have some correspondence, of course, through the right-hand side forcing in the resolvent, but that's not known. So what we can see from the spectrum, however, is that there is a sort of qualitative agreement over most of the different frequencies. There's the same ordering of the modes in terms of which axis symmetric, which azimuthal mode, m equals 1 to 5, has the dominant energy at any given frequency. This can be seen a little bit better by taking these line plots and sort of turning them into a heat map versus azimuthal mode in the jet. So this is Struhal number on the x-axis, azimuthal mode on the y-axis, and on the top plot, you're looking at the dominant SPOD eigenvalue. On the bottom plot, you're looking at the dominant resolvent gain. And what we've done here is we've normalized at each frequency, we've normalized the corresponding energy or gain by the sum over the first 5 azimuthal modes. So what that does is sort of equalizes the energy on these plots, so it's easier to visualize what's happening as we go down to the right, where we have low energy at low frequencies. And you see that these two maps give us very much the same picture of the dominant modes in these flows. And there's some interesting different regions of these plots. So the first one is near the 0 azimuthal mode, so low azimuthal modes, and over a range of frequencies from somewhere like 0.2 up towards 1, and probably even higher if we were to go higher. And what you see here, this is the velocity field plotted now. The top plot is from SPOD, and the bottom plot is from the resolvent analysis. And what you see is this wonderful comparison between these two predictions. We see a very precise agreement for this Kelvin-Helmholtz mode. So we might say from this analog between resolvent and SPOD that this mode is sort of forced by white noise, as it were. On the other hand, if we look at very low frequencies in the jet, we see a very different kind of structure, and it's dominating not now at the m equals 0 mode, but in fact it has its highest energy at m equals 1 and 2, depending on the frequency. And what we found here, we were rather surprised to see at first, and what we clearly see is a structure that is reminiscent of the lift-up mechanism that is also present in wall-bounded shear flows. So in the lift-up mechanism, you have elongated streamwise streaks. That's what these structures are, and that are produced by input modes that are counter-rotating vortices. And those counter-rotating vortices lift up low-speed fluid from below and push down high-speed fluid from above, at least in a boundary layer reference frame. So, so we're seeing these lift-up kind of structures in the jet in this particular frequency regime. And then when we go to some other frequencies here, like here, if we look at the very low frequencies, but the m equals 0 mode, we see another kind of wave packet structure, but it turns out to have very different properties from Kelvin-Helmholtz wave packets. We've called these OR modes for lack of a better terminology, because they have this standard kind of OR behavior of having a structure that tilts progressively as you go downstream in the shear. So these OR modes turn out to sort of underpin the entire jet spectrum. You can kind of find them all over this frequency domain, but they're not always the dominant mode. They only seem to be the dominant mode when either the Kelvin-Helmholtz or the streak mode are not present. So that allows us to sort of construct a frequency map of the jet that shows which physical mechanism is dominating in the generation of large-scale structures over different frequencies and azimuthal modes. So again, for low frequencies, but higher azimuthal modes, we have lift-up dominating. For higher frequencies and lower azimuthal modes, we have Kelvin-Helmholtz dominating. And the OR that we see here, you should really think about as being underneath this entire picture. There are OR modes everywhere. They're just only dominant modes when those other mechanisms are not at play. So the resolvent together with SPOD gives us this really much more complete view of the jet. So turning now to modeling the forcing in the resolvent analysis, I want to tell you now about this using eddy viscosity models for the forcing. Before I do that, I guess I have to come clean, because in the plots I've been showing you previously, where we see this lovely agreement between the resolvent analysis and the SPOD, I was actually using the eddy viscosity model that I'm about to show you in order to produce that lovely agreement between these two things. So this is not the level agreement that you would see if you used the molecular viscosity in the resolvent calculation. And I'll explain that now as we go along, why we think this eddy viscosity model has some predictive power in the jet. So eddy viscosity, using eddy viscosity for disturbance fields in either linear stability analysis or resolvent analysis is also not a new thing. It's been used really quite widely. But I really want to stress, because this is something that I think is important for the community to confront, is that there's no rational self-consistent basis for the use of eddy viscosity in this case. It's been justified based on the idea of an unsteady RANS, which in fact is not at all appropriate to the jet that we're looking at, for example, because that jet is stationary, it's steady. So the unsteady RANS equation should become steady in this case upon averaging. And the other technique that's often invoked is the triple decomposition, which is certainly an appropriate thing to invoke in a kind of qualitative sense. But in natural turbulence, there is no phase reference with which we can define a phase average. So in fact, unless you're happy with just using the triple decomposition without ever defining the average, and it's quite possible to do so, but it really then lacks a sort of self-consistent formulation of what it is that we actually mean by the coherent motions as opposed to the incoherent ones. So I don't really raise this as a critique of anybody that's using eddy viscosity. We're doing so ourselves here, but really as an open issue for the community to confront on how to develop an appropriate eddy viscosity framework for these coherent fluctuation fields. We have some ideas along those lines, but nothing that we've been able to get a lot of traction with. So I won't say more about that today. What I do want to tell you about is a kind of data-driven approach that we looked at. And this was work that Denny Sipp really helped us a lot with when he was doing a sabbatical at Caltech a couple of years back. So what we wanted to sort of figure out is how good of a model of the forcing is the eddy viscosity? How good of a model could it possibly be? So if we start with our Navier-Stokes equations without eddy viscosity, we have through the resolvent this forcing F that needs to be modeled that would give us the relation between the forcing statistics and the output statistics, the SQQ. What we do here is we put in the eddy viscosity ansatz and we ask the question, can we find an eddy viscosity field in this flow such that the resolvent operator amended to include the eddy viscosity gives the same output as the SPOD. So since we have the data from SPOD, we can in fact drive an optimization that tunes the eddy viscosity field in the resolvent analysis to get as close as it can to the SPOD modes. So I'll show you the results of that. I'll skip the whole sort of formulation. Oh, here's George. Hi, George. We'll skip the whole formulation of that, and I'll just show you the results because it's really quite remarkable how well a good of an eddy viscosity you can find. So the way I'm going to present these plots is with this alignment metric plot that I'm showing you here at the top left, and this requires a bit of explanation. So the alignment is plotted versus Struhal number. And what the alignment is it's a sort of the inner product between the resolvent mode with the eddy viscosity, optimized eddy viscosity field, and the first SPOD mode, right? The dominant resolvent in the first SPOD mode. So when those two fields align precisely, you get 1. And when they have no correlation, you get 0. So that's easy to understand, except it's not really easy to understand what 0.4 alignment means. So as I go through some pictures, I'll try to point that out, but generally an alignment above about 0.5 is actually quite good. If you look at two contour plots of something with an alignment on this metric of 0.5, they look pretty close to each other. What you see here is the black symbols are the baseline flow. So this is the resolvent analysis with essentially with the molecular viscosity, with a very small viscosity value. And what you see is that bumping up at about 0.2, we get not a bad alignment between the SPOD and resolvent modes. It's up here at about 0.7, even without the eddy viscosity. But for the low frequencies, the alignment is completely terrible, right? It's like 0.2. Now, the symbols here represent different optimal eddy viscosity models. So really, you only have to look at the top set of points here, the blue, the blue crosses. So this is the optimized eddy viscosity field, and you see that the optimizer can find an eddy viscosity field such that it drives this alignment all the way up to 80% across all of the frequencies. And we can understand why there's this difference between the low frequency behavior without the eddy viscosity and the higher frequency behavior by recalling that for the higher frequencies, we have the Kelvin-Helmholtz mode dominating. And where that Kelvin-Helmholtz mode is dominating, these structures are essentially Reynolds number independent over a fairly large range of Reynolds numbers. So the results there just aren't sensitive to whatever model you put in. The model helps a bit. You get from like 0.7 up to 0.8 or 0.9, so that's great. But it doesn't have a very large effect. The large effect is at these frequencies where you don't have this strong low rank behavior. And for this m equals 0 prediction here, these would all be OR waves in the jet. So the eddy viscosity is able to align even those OR waves. So the pictures here, if you just concentrate on the leftmost column, that's the lowest frequency where we see without the eddy viscosity model, the largest discrepancy. The top picture is the SPOD mode that we get from the data. The first picture down from that is the baseline case. So this is no eddy viscosity model. So you see those structures have nothing in common with each other. They have a different wavelength. They're amplified in a different region of the jet. And then the next 4 images down represent 4 different eddy viscosity models. Again, I'm only referring to the first of those in this discussion. And you see, again, this much better alignment between the third picture and the top picture. So that's an alignment on this plot of a value of about 0.8. It doesn't look so great near the beginning here. This is actually statistical error in our SPOD. These low frequency modes are very difficult to capture with a finite data series. So we understand why we have those problems there. So generally this looks very successful. So you could ask, okay, great. I mean, this optimizer finds some crazy eddy viscosity field. Of what possible use is that in modeling? Well, we have kind of 2 answers to that. First of all, it didn't find a crazy eddy viscosity field. When you look at the optimized eddy viscosity field, it's quite reasonable physically. But the more important point, and this brings in these other models that we looked at here, is that the results are fairly insensitive to the details of the eddy viscosity model. Even using just a constant viscosity, but optimizing its value can bring the alignment up substantially. And so in fact, what we're able to do is just use straight up RANs to be able to infer the eddy viscosity field. So we made a subsequent computation of the same turbulent jet that we had the LES for. We did that with a K epsilon RANS model using Fluent. We did a bit of fiddling, to be honest with you, to get the mean field from the LES and the mean field from RANS to be as close as we could get them. We wanted to sort of give the fairest possible comparison for the fluctuations. And we chose a single calibration constant over all frequencies and azimuthal modes for that eddy viscosity, and then put it into the resolvent. And what happens is shown on the pictures at the bottom. We take the baseline case at the right, where only the m=1 mode is sort of pretty well aligned in the natural case, and then only over a certain frequency. All these other azimuthal modes have very poor alignment in the baseline case. And you see that even with this fairly lightly calibrated RANS model straight out of K epsilon prediction, these all bump up to much higher values. They're not as good as the optimal field, especially at the lowest frequencies, but they're much closer to sort of acceptable values to be able to say that we have some quantitative agreement between the prediction here, the resolvent, and the SPOD. And I just want to point out for doubters that, you know, we're predicting coherent structures in a turbulent flow. I was very happy to get a 0.8 alignment between those two fields. It really is kind of remarkable how well this very simple eddy viscosity model works. So I'll leave that topic now. As I said in introducing it, the sort of the state of these eddy viscosity models for resolvent is not great in the sense of, you know, we don't really have a rational, self-consistent framework for the eddy viscosity yet. But even so, when we just sort of use this ad hoc eddy viscosity model, things do work out pretty well. So in the last part of the talk, I want to show you work that really was mostly done by George Regas and Denny Sipp. Again, when Denny was visiting Caltech was when this project got launched. So in some discussions, we were wanting to see if resolvent analysis could be used in some kind of nonlinear setting. And the setting that we chose for this was thinking about transition prediction. So the reason we wanted to look at this area is because there's this huge gap between sort of engineering practice in transition prediction and academic work. So on the engineering side, we have empirical methods like e to the n that are still dominating. And on the academic side, really, you know, arguably the only thing we have is DNS, which of course is very expensive. But more importantly, with DNS, you always have this problem when looking at transition of how should you force the DNS. And you basically need to do DNS in some kind of an optimization mode in order to discover what is the most dangerous perturbations that lead to the fastest transition. Now that question itself has been addressed already over a number of years, you know, starting with early work where, for example, we have the K-type and the H-type transition paths that involve the Tolming-Schlichting waves interacting with oblique waves in the boundary layer. And in more recent times, we have the non-modal kinds of analysis that tells us that we don't really need TS waves to have transition scenarios. We can excite them with oblique waves, which if they grow to nonlinearity, break down in streaks and so on. So, you know, I'm not trying to portray this that we don't know anything about these different transition scenarios, but it's very difficult to predict them reliably. When we think about doing so, we can break things up into techniques that are using the time domain versus using the frequency domain. So in the time domain, when we're thinking about optimal perturbations, we're sort of asking the question, what is the what is the most dangerous initial condition? And when we're thinking about the frequency domain, we're thinking what is the kind of most dangerous forcing field for the fluctuations. And I should mention that in the frequency domain here, this is exactly the same resolvent operator that we were talking about in the turbulent case, but now it's the linearization about a laminar flow rather than a turbulent mean flow. So in the linear side of things, of course, these are calculations that have been now reliably made for a number of years. And So for example, you can map out these non-modal mechanisms and you can find over which sort of spanwise wave numbers beta on the y-axis and what frequencies here we get the largest linear amplifications. And you see that there are sort of two peaks here for the boundary layer. There are streaks that are, large values of beta and low frequencies. And then there are oblique waves that are high frequencies and small values of beta. So both of these suffer growth, but in the linear analysis, the streak mode sort of dominates. So what happens when we turn our attention to the nonlinear world? Well, here, there's work using essentially DNS and optimization techniques to solve this problem. And so you have these really beautiful results where in periodic domain flows, at least, we can find these worst case initial conditions that lead to maximal amplification, and in this case, lead us to these very beautiful and interesting edge states of turbulence. So these calculations are marvelous, but we really want to try to fill in this last block of how to do the nonlinear analysis in the frequency domain. And part of the reason is to try to connect with the engineering literature where we're interested in spatially developing flows. An engineer can't really make use of the information of what is the worst initial condition when the initial condition on the airplane is always long forgotten. So it would be very nice to be able to look at this sort of minimal seed problem or optimal disturbance problem in the frequency domain and with nonlinearity. So the technique that we implemented for this is the harmonic balanced Navier-Stokes equations. These are basically just the Navier-Stokes equations written in the frequency and spanwise wave number domain and Fourier transformed into those two spaces. So you get this huge coupled elliptic system of equations that you need to solve for the disturbances at each frequency that are coupled through the nonlinear terms to all the other frequencies and azimuthal mode numbers. So George very patiently programmed this all up and wrote a really creative solver to be able to invert this system and do the optimization using a Jacobi iterative GMRes, a GMRes with a block Jacobi preconditioner. So again, I'll skip over really all the computational details on that because I want to have a few minutes to show you about the kind of interesting results that this model delivers. So this is just a validation case to make sure that everything's been programmed correctly. What we're comparing to here is the direct numerical simulations of Rist and Fossil, where they looked at a K-type transition scenario where they had a domain that had was mimicking an experiment that had a blowing and suction slot, and the forcing on that slot was being forced to get this kind of K-type transition, so a steady 3D disturbance on top of a TS wave. And without going into the physics here, which are interesting, but beside the point for this plot, this is just to show you that the harmonics that are generated in this frequency domain solution match very, very closely with the DNS predictions that were computed in the time domain. So that gave us an enormous confidence that everything was implemented correctly. So we went on to try to do the resolvent problem now to actually carry out this optimization. So this requires some choices to be made. We need to decide what cost function we're going to try to maximize to represent the transition process. Excuse me. And the one we settled on was looking at the integrated wall shear stress on the wall. And in fact, the difference between that and the laminar value. So we're going to try to drive the shear stress to the largest possible value, constrained by satisfying the harmonic balance equations, of course. And in the nonlinear case, you also have to constrain the amplitude, right? Because I could always get an immediate transition by just putting in disturbances at a very high amplitude. So we're going to take the overall norm of the forcing function to be an input to the problem, and we're going to constrain the solution so that it never puts in more energy than the amount A. So unlike a linear problem, we have this extra degree of freedom, the amplitude of the disturbances. So I'll just show you a few results from this. If you're interested, George has a manuscript that he is, I think, is accepted or nearly accepted in JFM. So he'd be happy to share that with you. I'll just show you a few results from this. In the first case here, we're just forcing 3 modes. So we're forcing one 0 frequency, non-zero beta mode, one 0 beta and non-zero frequency mode, and one that involves both a non-zero frequency and a non-zero wave number. And we're only allowing a response in the black modes here in the beta omega space. So this is a highly truncated calculation. I'll say more about what happens as you add more modes in a few moments. But in this highly truncated Navier-Stokes solution, we then choose a constant A, and we drive this optimization to find what forcing field we should add in order to maximize the growth of this wall shear stress. So those results are plotted on the right. The contours here are sort of the change in drag coefficient on the plate. And this is plotted as a function of the frequency omega 1 and so that's the fundamental frequency, the frequency of this first mode that's being added, and the spanwise wave number beta 1, right? So each point on this plot represents a whole separate optimization where the harmonics are slaved to this fundamental mode, right? So we can see where in the frequency domain and where in the wave number domain we get the maximal growth. And interestingly, you get this region of the oblique waves rather than the streaks as now being the dominant. So if you contrast this with the linear plot that we saw a moment ago, that's a key difference in the nonlinear case. But interestingly, this is the cost function, but when you look at the actual forcing and response that this achieves in the solution, what you find is that these oblique modes have, through nonlinearity, excited the streaks. So even though we're forcing here, we get energy in the streaks. This was now done over a range of different amplitudes, and in keeping the forcing modes the same, but now allowing the response to occur at more and more harmonic frequencies, more and more power, more and more factors of 2 multiplied by the fundamental modes. And so we wanted to see several things here, right? We wanted to, first of all, make sure that these results were convergent in some sense, right? That we weren't truncating too severely. And so what you can see on this plot, again, I'm going through this pretty quickly, so I apologize for all the detail here, but if you take a constant amplitude on this plot, what you can see is that as you add more and more modes, as you go up this plot, you do see sort of a convergence. But again, if you go this way on the plot, you can always find an amplitude for which our ansatz is giving up, right? Where we're generating more and more harmonics through nonlinearity such that our series is no longer converging. So we have to be mindful of that when we're looking at these results. But looking at those amplitudes that are less than this threshold and looking at retaining the higher number of modes here, we can see that we get this actually very strong growth in the skin friction towards the end of the domain. And you can see now a transition process where the streaks are further breaking down into hairpin vortex structures. And so if we continue that now, and we look at 2 cases, so in the plot I just showed you, we were actually imposing a spanwise symmetry. So the minus beta modes were slaved to the positive beta ones. That results in this kind of varicose streak instability. And if you remove that symmetry, so you allow the negative wave numbers to be whatever they want to be, then in fact you actually get the transition occurring through the sinuous kind of streak instability, again forming these kind of lambda vortices further downstream. And again, you see this accompanying shoot up value in the skin friction coefficient that looks like it's going toward the turbulent state. And for some of these calculations, when you look at them closely, they're really kind of remarkable. So in the case where we take away the symmetry, for example, if we look if we look at how the boundary layer profile is developing as we go downstream, we can actually see the formation of what looks like a nascent log law in this velocity profile. So with just a few harmonic modes being retained in the equations, we have kind of a nascent turbulent boundary layer. So this is maybe something like an edge state, but in this kind of spatial framework. So with that, I need to close. I see I'm running late here on time, so I'm going to skip through the summary. I just want to make a few points about some of the things, some of the places we still need to go. I haven't talked much about computational technique here. It's not the most exciting thing to talk about, but one thing we have to confront in resolvent analysis is that we're maxing out our computers with today's calculations of doing resolvent analysis on two-dimensional base flows. The memory constraints on the computer are very, very severe in this case. And in the example you just showed where we actually want to do this nonlinear simulation, the situation is even now much worse. So there's a strong need for approximate techniques that would speed up the calculations. And I just want to highlight one of them that we've been working on now for a number of years in the group. Aaron and George and a new student, Omar Kamal, have been contributing to this. And this is a technique we call OWNS, or one-way Navier-Stokes equations. So OWNS is a kind of PSE-like technique that parabolizes the equations, but unlike PSE, it's actually a convergent approximation. And through that convergence, you can do a number of things like nonlinear analysis that are actually quite difficult to do with PSE, because PSE is always kind of on the edge of blowing up. So this is just something that I wanted to kind of advertise as a path forward to doing resolvent on larger and larger flows that are represented by more and more grid points, basically. So thank you for listening at this either very early or very late hour, depending on where you are. I will close with that, and I would be happy to stay on as long as anybody would like to answer questions.
Okay, let me thank you on behalf of everyone for a very interesting talk, Tim. If anyone wants to ask a question, if you want to raise your hand. While people are raising their hands, if I could ask something quickly. In the last part on the transition problem, I mean, a lot of people believe that it's the receptivity problem, which is a problem which is the missing link in being able to predict transition in aerodynamic situations. I mean, I think there are lots of ways to do the linear growth and then the non-linear breakdown. And the kind of optimal disturbance is maybe not that relevant. I mean, it's actually what the fluid can actually generate on the wing, which matters rather than what could possibly be generated.
Right.
So I mean, I think the missing link is maybe
right. It's a great point. It's a great point you're raising, Phil. I mean, and I certainly agree with it. You know, we are solving a receptivity problem here with the optimization, but we're not restricting our disturbance field to a sort of physically realizable set of disturbances or a set of likely disturbances. So these are things that need work in the community in order to, you know, sort of properly define. It doesn't seem to me that it's impossible to do so by thinking about this this input matrix C and where it comes from, and by you know, confronting data and so on with these approaches. I think we might be able to move towards those problems.
Yeah, I mean, in a sense, the optimal approach is too strict, as it were, for industry, because it's a worst case scenario which maybe could never be realized.
Yeah, that's right. I mean, but if I have no other information, I'll take the worst case, right?
Yeah. Do we have more questions? I think you stunned them into silence.
Yeah, I'm going to go with the question.
Go ahead, Hugh.
So, You never showed us what these optimized eddy viscosity fields look like. I was kind of interested to see that. You able to show us any of that?
I don't think I have a picture in this set, Hugh, and it would take me maybe a few minutes to dig it up. I can send them to you, but let me just tell you that they're, you know, so one thing I maybe didn't mention is that we're restricting that eddy viscosity field. I mean, we're associating with the mean, and because the mean in this case is steady and axisymmetric, we're finding a steady axisymmetric eddy viscosity field.
Yep.
And beyond that, it looks a lot like the one that you would infer from RANS. So the optimizer isn't really doing that much other than you know, increasing the eddy viscosity in that part of the shear layer where the RANS model would already have had it. So it really didn't turn out to be we thought that was going to be an interesting thing, but it really didn't turn out to be that interesting. And I think it's really a favorable result that it isn't interesting, because if it is interesting, that means it's going to be difficult to model. So so the lesson there was that you know, as well as the eddy viscosity model works, and of course that's debatable, right? I'm not trying to imply that this is going to give you very, very good predictions, but it's as good as the RANS, is what I would say.
Okay, thanks.
Do you have more questions?
I see Vasilis has a hand up.
Oh, sorry, I missed that.
Yeah, I do. Yeah, thanks, Tim, for the nice talk. You did at the beginning mention the challenges of the size and some new work that Oliver is doing. Can you please give us some more details on that?
That was with respect to doing SPOD, and I think if I'm picking up what you're asking about correctly, and that's the streaming algorithm. So that's very similar to eigenvector updating algorithms, streaming algorithms, and borrows that same machinery. So you know, there's nothing really. Well, I mean, you know, it's a nice piece of work. I don't mean to be implying that it's not, you know, what I'm trying to say is it's a pretty safe algorithm, right? It converges with understood properties to the SPOD modes. So that allows you to not have more than one block of data in core at the same time, right? So
that's massive, right? That's really important.
Yeah, it's important if you want to do this for like a large, you know, PIV data set. If you really want to do like 3D data. So all of our data we've done here is actually transformed in space to a 2D problem, right? So we're not pushing we don't need any streaming algorithm for any of the work I'm showing you here. But to do this in 3D flows, you would need that for sure.
Thanks.
Yeah.
Do you have more questions? The one way Navier-Stokes, was that for compressible flows or for incompressible?
It's formulated on the compressible equations. You know, we've taken it down to essentially incompressible limit, Phil, and we've also gone up to hypersonic speed. So I don't think there's any real limit there.
Yeah, I remember you talking about the compressible version a couple of years ago, but
yeah.
I hadn't seen the incompressible.
Well, it's not, we don't formulate that separately. So when I'm saying incompressible, we're doing like Mach 0.2 or Mach 0.1, right?
Yeah.
So it's the same equations either way.
Okay, well, if there aren't any more questions, let me thank Tim again for a stimulating talk. And
let me thank all of you for listening. I know it's not so much fun as it used to be in these formats, but I really appreciate everybody checking in. So thank you.
Thanks, Tim. It was really good.
Yeah, no, the timing is worse for you than anybody, I think.
Okay, Tim.